So our primary focus today is going to be on the oxidation reduction reactions and learning how to recognize those reactions when they occur and how to balance those reactions, because the balancing of these reactions is a little bit different. Because electrons are moving, and because we are dealing primarily with net ionic equations and these electrons moving, we have to account for another dimension of balancing that we haven't thought of before. So thus far, all we've been concerned with has been the balancing of atoms, because we've assumed that with molecular equations, and this is the case, when we have molecular equations, we can assume pretty safely that the charges, because they are balanced by the molecular equations, the charges are already accounted for. In redox reactions, because we are not dealing with molecular equations, because we are dealing with net ionic equations instead, what we're going to find is that we are going to have to account for charge in addition to atoms when we think about balancing equations. And so there's a slightly different process that's involved here. And there are two primary methods of doing this reaction balancing. I'm going to show you one way which I feel is superior and involves fewer steps and generally allows you to solve the problems more quickly and with greater accuracy. The issue with it is that you have to know your oxidation numbers pretty well. You have to be able to assign oxidation numbers quickly and accurately in order to use the method I'm going to show you. In the second half of today's lecture, I will show you the alternative method called the half reactions method. Is the method that I learned when I was in high school and then in college. It's probably, if you've seen this before, it's probably the method you were taught. The problem with it is that it's very deliberate. There are many steps to it. And there is the problem that with many steps and how slow it tends to be, there are chances to make more mistakes along the way. But on the flip side, you don't need to know oxidation numbers to do it. And it does come in handy. One of the primary applications of this kind of balancing comes when you do electrochemistry. So for those of you that have to take General Chemistry 2 at a later time, that does translate into half reactions. And the half reaction method that I'll show you in the second half will show that, will bear that. So just something to kind of keep in mind, think about. But let's just kind of go back and review a little bit about redox reactions before we actually get to the balancing. So if we follow from our discussion yesterday, what we should be able to see is that we can assign oxidation numbers to all of these reactants involved. Now, notice this is a net ionic equation. I've got zinc reacting with copper 2 plus. Now, the copper 2 plus would not exist as copper 2 plus other than in aqueous solution. How we got the copper 2 plus is we dissolved something like copper 2 chloride or copper 2 nitrate or copper 2 sulfate in water. And that's how we got the copper 2 plus to be available in solution. But nonetheless, we take that zinc, we react it with the copper in the solution, and it gives us zinc ion and copper metal. Now, from an oxidation number standpoint, we know that the zinc, being that it is an element, has an oxidation number of 0. The copper 2 plus, being a monatomic ion, has a oxidation number of +2. Zinc being a monatomic ion, its oxidation number is the same as the charge also, so +2. And copper being an element has an oxidation number of 0. Furthermore, we can see that as far as the zinc is concerned, its oxidation number is going from 0 to +2. Now, to go from 0 to +2, you would have to lose 2 electrons along the way. And so, as a result, we know by definition that the process of losing electrons is oxidation. Again, think about your mnemonics. Leo the lion goes grr. Leo, loss of electrons is oxidation. On the flip side, we know that the copper went from a +2 state to a 0 state. The only way to do that would have been to gain 2 electrons along the way. So we know that by definition, again, a gain of 2 electrons, Leo the lion says grr, gain of electrons is reduction, that the copper has been reduced in this process. Now, what about these other two terms here? We've got two other terms that are being thrown at us here: the reducing agent and the oxidizing agent. Now, what are those? Well, in simplest terms, the reducing agent is the reactant that contains the element being oxidized. In other words, is the reactant that forces reduction. That's what a reducing agent is. So we can look at it in either of those two ways, in either of those two lights. We're either seeing something that forces reduction, or we can think about it as the reactant that contains the element being oxidized. And so one of the most common mistakes made in this particular realm is assuming that the element itself is the reducing agent or the oxidizing agent. Now, for oxidizing agent, we can talk about the reactant that contains the element being reduced, or the reactant that forces oxidation. And both of those definitions would be considered valid. The important thing to remember is that in both cases, we are talking about a reactant, not an individual element. So oxidation and reduction occur on an individual elemental level. The zinc is what is oxidized. The copper is what is reduced. But in terms of oxidizing agent and reducing agent, the zinc metal is the reducing agent. The copper 2+ ion is the oxidizing agent. And this is a simple example, so it's not as difficult to get them kind of confused. When we see other more complicated oxidizing and reducing agents, it is going to get a little bit more muddy because there will be other elements involved in each of these. So keep that in mind. And so this is the terminology. These are the definitions that your book gives you. So again, the oxidizing agent is the reactant that forces the oxidation of another reactant. And like I said, I would change the wording here. To say an element in this substance will be reduced. Because again, the entire substance does not get reduced, but an individual element within it will. And we can do the same thing down here. An element in the reducing agent will be oxidized. So the reducing agent is the reactant that forces the reduction of another reactant. So it seems like it's kind of backwards, but the key words in all of these is the force. An oxidizing agent forces oxidation. A reducing agent forces reduction. And since the two processes are tied together, then inherently, that means that when that oxidizing agent forces that oxidation and rips those electrons away from something else, those electrons go somewhere, and they go somewhere to one of the elements inside of that oxidizing agent. So let's get into a problem like this then. Here we have hydrazine, N2H4, reacting with dinitrogen tetroxide, N2O4. And the reaction produces nitrogen gas and water vapor. And this is the primary reaction that has been used for many, many decades for the propulsion of rockets and other things in space. This is the reaction that ultimately allowed our astronauts to go from the Earth to the moon and then back again. This is, if they have to do any kind of getting around, this is what they do to set themselves up for re-entry angles, the whole thing. So this is the reaction that takes place. Now, the question is, what is oxidized? What is reduced? What is the oxidizing agent? What is the reducing agent? Now, to that end, what we need to look at first and foremost are the oxidation numbers for each of the elements in this reaction, because that's going to tell us what happened. And so, if you recall, the way to do this, if I have hydrogen, remember each hydrogen, if it is bonded to a nonmetal, is +1. So hydrogen's +1. The nitrogen would have to be -2 to contrast that. Again, the way you can set it up is 2 nitrogens plus 4 hydrogens is equal to the total charge of 0. We don't know what nitrogen is, but we know that each hydrogen is +1. So if we continue our algebra, that's how we arrive at the -2. If we keep going, again, each oxygen here is -2. So that means that the nitrogens here are +4. This is elemental nitrogen, so the oxidation number for all of the nitrogens there is 0. And then we have a -2 for the oxygen and a +1 for the hydrogens here. And so what we need to do is we need to do comparisons. So I compare. My hydrogen was +1. It's still +1. So from a redox standpoint, even though we had a rearrangement here chemically, electronically, nothing happened to the hydrogen. Same thing for the oxygen. -2 here, -2 here. Even though we saw a reaction, electronically, nothing happened to the oxygen. But here, we see that we have a -2 for the nitrogen, turning into a 0 here. And what's even more interesting is that we have a +4 for the nitrogen here, turning into a 0 here, because this is the only nitrogen in the product. So what we have here is an interesting circumstance. We've got 2 different compounds containing nitrogen, And the nitrogen in each case is being the thing that is being oxidized or reduced. So how do we handle that? What does that look like? Well, we can see that as far as oxidation is concerned, it is the nitrogen in the hydrazine that is being oxidized. Because we're going from a -2 to a 0 state. So every nitrogen in hydrazine is losing 2 electrons. And for the dinitrogen tetroxide, we see that the nitrogen in that is being reduced because it's going from +4 to 0 also. So when we are identifying elements that are being oxidized or reduced, this is how we would do it in this particular case. Nitrogen is the answer to both of them. To differentiate them, we would talk about the nitrogen in whatever compound it is. So the nitrogen in hydrazine was oxidized. The nitrogen in dinitrogen tetroxide was reduced. Now, to assign oxidizing and reducing agents, we would have to take this one step further. Remember, oxidizing agents force oxidation. So the N2O4 is the oxidizing agent. It is forcing the oxidation of the nitrogen in the hydrazine. And the hydrazine is the reducing agent. It is forcing the reduction of the nitrogen in the dinitrogen tetroxide. So that's how we attack these kinds of problems. We have to assign oxidation numbers, figure out where the electrons are going, and once we've figured out where the electrons are going, then we can determine, okay, this was oxidized, this was reduced, this compound or substance forced the oxidation, this substance forced the reduction, and what we will see is that it kind of has a crosswise effect. The thing which is oxidized is the reducing agent. The thing that is reduced is the oxidizing agent. So any questions about this before we move on to more complicated matters?
No.
All right. Then let's continue on with the idea of redox reactions and balancing those reactions. Now, as I said in our introduction today, our primary focus is going to be using something called the oxidation number method. The oxidation number method is my preferred way of balancing these equations because so long as we don't have to break them apart into half reactions, this will balance the equations far more quickly, far more easily than anything else will. And so to that end, they are way more useful. But they are a little bit more difficult in terms of you really have to have your oxidation numbers down. You have to know what you're doing there. Now, in the second half of today, we will talk about the half reaction method. You don't have access to the learning lab, so I'm going to take care of that myself. We'll take probably about half an hour or so at the end of today's lecture to talk about that. And the half reaction method does have some utility. Again, if you end up having to take Chem 2, when you do the electrochem unit, the half reaction method is how electrochemical reactions are presented. But like I said, for our purposes here in this course, we usually just have to balance reactions, and the oxidation number method is a good deal faster. So let's get into what the method looks like. From the methodology standpoint, what we're going to have is a skeleton reaction. Now, the skeleton reaction is going to be a net ionic equation, where we start with 1 mole of each reactant that's relevant and 1 mole of each product that's relevant. So we saw examples of that in the previous couple of problems, where we had copper metal and copper ion, zinc metal and zinc ion, and we didn't concern ourselves with what those spectator ions were. That's the skeleton reaction. Now, the second step in this is to do what we just did in that hydrazine example. And in the hydrazine example, the first thing we did was we assigned oxidation numbers to everything. And that's exactly what you're going to do in this case as well. The only difference is that in addition to doing the oxidation numbers, you're going to calculate the change in oxidation number for each element. And we kind of did that, but not nearly to the same degree. The thing that's different is we are going to calculate the total change in number for all atoms of the element. And that's going to be the important difference for us. So in the case of the previous example where we had the hydrazine and we were doing all of that, we only said, okay, the +4 here is turning into a 0. And so it had to, we had to take in 4 electrons. In the balancing part, we would say, okay, well, hold on a second. There are 2 of those nitrogens. Each one gains 4 electrons. So 2 times 4 would be 8 electrons in total that need to be gained. And then we would do the same kind of thing for the nitrogen here. I had 2 nitrogens that were each losing 2 electrons. And so the reason this 2 is out here is to balance that out and get the totals to work out correctly. So we'll hit that spot here, because the next step is, once we've figured out the total change in number, now we're going to use coefficients to balance out that change, because the most important thing in a redox reaction is that we have to have a balance of charge. And that means that every single electron that is lost by the thing that is oxidized needs to be absorbed by the thing that is reduced. And so there can't be any electrons left over in either direction. I can't have a reduction that requires 9 electrons if the oxidized species only gives up 5. I'm going to have to balance that out in some kind of way. And so coefficients are going to be the thing that ultimately does that. Now, in the process of doing that, every element that is not hydrogen or oxygen will also be balanced in the process. And then finally, the last 2 steps kind of run into each other. Step 4 is we're going to balance the total ionic charge on the reaction by either using hydrogen ions if the reaction is occurring in acid, or hydroxide ions if the reaction is occurring in base. That'll fix the charge issue, and then we'll use water at the very end to fix the hydrogen and oxygen issue. And normally speaking, that change, step 4 is probably the most difficult of the, because we have to get it right and we have to make sure that we calculate our charges correctly. Once we do that, though, the last step's usually pretty intuitive. And more often than not, we can base it on the hydrogens. So, you know, if I add 12 hydrogen ions to the product side, I'm going to need to add 6 waters to the reactant side to give me those 12 hydrogens back. It's usually something along those lines. It's pretty intuitive. And that's it. That's the entire process. It all fits on this one slide. But the best way to go about this is to do a number of examples, and that's where we're going to be today for the most part. So in example 6 here, I've got a nail. It's made out of solid iron. I put it into a solution of a soluble palladium-2 salt, and the nail starts to disappear as the iron enters the solution as iron 3+. What is the redox reaction here? Well, the first thing that we would do is we would set up that skeleton net ionic reaction. I've got iron in the solid phase reacting with palladium. And I know that it's palladium 2+. And I know that it turns into iron 3+. And it doesn't tell us, but we're pretty safe to assume, because palladium only has 2 well-known oxidation states, that the other state here is going to be solid palladium. So my first step is going to be to, now that I've got my skeleton reaction, is going to be setting up my oxidation numbers. So I've got iron here. Iron is in an elemental state, so its number is 0. Palladium is monatomic ion, so its charge. Same with the iron. This palladium is in an elemental state, so it is a 0 state. I've now assigned all of the oxidation numbers. Now I need to go about assigning changes in oxidation number. I'm going from a 0 state to a 3 positive state. In the iron, 0 to positive 3 is an indication that I have lost 3 electrons. Palladium is going from a positive 2 state to a 0 state. So that means that it has gained 2 electrons. Now, in this case, since I have 1 of each of these, I don't have to do anything else with it. The total movement of electrons is the same as the change of oxidation numbers. The only thing that is left to do is I have to balance out the movement of these electrons. I have 3 electrons being lost by the iron, but only 2 electrons coming back to the palladium. So the way to handle this is using a lowest common multiple. Lowest common multiple between 3 and 2 is 6. So I'm going to multiply each one of these reactions by a number to get it to 6 electrons in total. So 3 times 2 will give me 6 electrons lost. 2 times 3 will give me 6 electrons gained. And these multipliers are going to become our coefficients in the equation. So the iron gets a 2 here and a 2 here. And the palladium gets a 3 here and a 3 there. And so from this standpoint, I've now balanced. My irons are balanced. I've got 2 on each side. My palladiums are balanced. I've got 3 on each side. And because of this calculation, I now know that I have an equal number of electrons leaving the iron as being taken in by the palladium. Now it's just a matter of determining total charge. To determine total charge, we do something very similar to what we did when we first started balancing equations. We split this sucker in half. The total charge on iron is 0. The total charge on palladium is +2. 0 plus +6 is +6. So the total charge on the reactant side is +6. On the product side, I have 2 iron 3 pluses, so 2 times +3. I have 3 palladium zeros. So now I have 6 plus 0, so +6 over here as well. Since the total charges are even, no further balancing is required. So we didn't even need to do the last couple of steps where we had to deal with hydrogen and oxygen. There is no hydrogen and oxygen in the equation currently. We have an evenness of charge, so we don't need to add anything. What this also means is that this particular reaction is equally likely to occur in acid, base, or neutral solution, which is an important thing to know. Now we will find this to happen more often in acid just as kind of a default, but it doesn't have to be. But the important thing to remember with the balancing of this equation is you had to balance both the charge and the atom. If I had gone back and just did this the way that we used to, no oxidation numbers, nothing of that sort, we would have probably looked at this and said, it's balanced already. I've got 1 iron on each side. I've got 1 palladium on each side. The problem with that line of thinking, obviously, is that we haven't accounted for the charge. And that's important because in a net ionic equation, charge hasn't been considered up until this point. So all of this stuff that we did is actually relevant because we needed to account for the fact that it wasn't just atoms rearranging here, it's the literal transmission of electrons from one element to the other. So iron is literally giving its electrons to the palladium to ion here. All right, any questions about this example?
No.
All right, then let's go and look at another example here. So in this example, we are given the oxidation of chloride by perchlorate ion. And we're asked to balance the equation in both acid and in base. Now, with the oxidation number method, this is actually pretty easy to do because the first few steps are identical, and it's only the last 2 steps that we have to change anything. So let's approach it from the standpoint of just generally speaking, let's start to balance this equation. And to that, I'm going to need to assign oxidation numbers. Oxidation number for chlorine in perchlorate is +7. The oxygen is -2. The oxidation number for chloride is -1. The oxidation number for chlorine in the chlorate ion is +5. Oxygen is still -2. And then chlorine here is going to have a 0 number. Now, one of the things that you can do that help a lot is oxidation and reduction usually kind of show up in terms of matched pairs. So if I want to figure out what happened to the chloride, the best course of action is to look at, okay, what happened in the chloride here versus here? This is what we would call a matched pair. The difference between them is only 1 oxygen or 2 oxygens or something like that. Whereas the chloride and the chlorine here, that's another matched pair. I'll actually change their color here to make it a little bit easier to see. They're another matched pair because neither of those species have oxygen. Now, one thing that we need to fix before we move anywhere near forward here is we need to fix the fact that my chloride here has only 1 chlorine, but its partner has 2. And so before I do anything else, I'm actually going to fix that right now by putting a preliminary coefficient in there to show that the chlorides become chlorine and that there are 2 of them that have to react. I have to have 2 chlorides in order to make a chlorine molecule. If I skip this step, the rest of my math is going to come out as half done. And I'm going to end up with the wrong answer because it's half done. And I'm going to end up not being able to balance the atoms. So from this perspective, now again, looking at the concept here of matching pairs, I can see that in the pink pair here, we have 2 chlorines going from -1 to 0, which means that a total of 2 electrons are lost. Each chlorine in this scenario loses 1 electron. There are 2 chlorines in total, so 2 electrons are lost overall. And for the blue scenario, I can see that I go from +7 to +5, which means that 2 electrons have been gained. So since this is the case, what I can also see now is that my electrons gained and my electrons lost are equal to each other. So I don't have to do anything more with coefficients here. The only thing I'm going to do is rewrite this equation just so it's a little bit easier for me to see all of the charges that are involved. So I'm going to put this in here. I have the perchlorate ion reacting with 2 chloride ions to make chlorate, and chlorine. So there's my reaction thus far. Now, the next thing to do, I need to evaluate total charge. Total charge, I have a -1 for the perchlorate plus 2 -1s for the chlorides. -1 plus -2 gives me -3 total. On the opposite side, I have a -1 ion for the chlorate and a 0 for the chlorine. That's a -1 total on the product side. Now the next step here is to fix the total charge. And how we fix the total charge depends completely on what we're doing. Are we in acid or are we in base? If we are in acid, we're going to add hydrogen ions. If we are in base, we're going to add hydroxide ions. So since we're doing acid, let's do acid first. And if we're doing acid, we're going to need to add H pluses. Adding positive ions means we're going to have to make one side more positive. So we're going to pick on the side that's more negative. To turn -3 into -1, I need to add 2 H plus ions. If I do that, my -3 becomes a -1, and now it matches. Now to counterbalance the adding of the H pluses, I'm going to have to add a number of waters to balance out the hydrogens, and it'll just take one. 2 hydrogens come from 1 water, so 1 water molecule will make the difference. And so my balanced equation in acid is going to be the perchlorate ion plus 2 chlorides plus 2 hydrogen ions yields the chlorate ion, ClO3 minus, chlorine, Cl2, and water. And that's really all there is to that. And so this is the reaction if it occurs in acid. Now, what if we were in base instead? Well, everything up until this point here would be exactly the same. We would evaluate the total charges. The only difference would be how we handle the balancing of those charges. Since we are in base, we would add hydroxides. And so we would need to add hydroxides to the less negative side to make it more negative. And so if I add 2 hydroxide ions here, that would turn my -1 into a -3, which would make it equal the -3 over here. As before, I added 2 hydrogens over here, so I need to add a water molecule over here to balance out those hydrogens that were added. And then I rewrite. perchlorate plus 2 chlorides plus water makes chlorate, chlorine, and 2 hydroxides. Again, this would be the balance if it was in base. So again, the beauty of this particular system is that it works, and up until the very last step, up until this spot right there, where we add the hydroxides or the hydrogens and the waters, up until there, it is exactly the same process either way. It's just getting to that spot. That's kind of the more difficult part. You really have to have your oxidation numbers down. You have to be able to set it up correctly. And so that's where you can really run into problems, and that's where a lot of people can end up struggling with this. Any questions here about example 7?
Not really.
All right, let's clear the deck then and do another example, and then we'll go ahead and take a break. All right, in this example, we have the iodate ion reacting with sulfur dioxide to make iodine and sulfate ion. And so we start exactly the same as we did in the previous problems. We need to assign oxidation numbers. Iodate in this is +5. Oxygen is -2. The sulfur is going to be +4. The oxygen is going to be -2. The iodine is going to be 0. The sulfur in sulfate is +6 and -2 in oxygen. And so setting up the matched pairs here is pretty easily. There's only 2 substances that contain iodine. There's only 2 substances that contain sulfur. So this one isn't as difficult to do. Let's just go ahead and box those in. We'll choose blue for the iodine. We'll choose pink for the sulfur. One other thing that we should look at and point to as far as the iodine is concerned, notice again that we have 2 iodines in my product, but only 1 here in the reactant. So before we do anything else, let's even that out so that we know and that we're working with the same numbers of each species. So now with that in mind, I can see that for the iodine, I'm going from 2 versions of +5 to 0, which means that a total of 10 electrons have been gained. Each iodine going from 5 to 0 means that it gained 5 electrons. The fact that there are 2 of them that underwent that, 5 times 2 gives me that 10. if I look at the sulfur, I can see that the sulfur is going from +4 to +6. There's only one sulfur in here, and so 2 electrons are being lost by the sulfur in this case. And so this presents for us a dilemma. Iodine requires 10 electrons to go. The sulfur is only capable of giving it 2. So what has to happen is that the sulfur reaction has to occur 5 times to give us those 10 electrons lost overall. And so that's going to come in the form of, we need to put a couple of 5s in here around the sulfur-containing atom substances to give us 5 sulfurs to react and lose the total of 10 electrons. So we've handled the first couple of steps. We have evaluated the oxidation numbers. We have evaluated the total number of electrons moving. We have added coefficients to make sure that all the electrons leaving are absorbed and vice versa. Now let's rewrite to be a little bit more clear. I have 2 iodates reacting with 5 sulfur dioxides to make iodine and 5 sulfates. The next step in the process is to divide the reaction in half and evaluate total charge. So I have 2 -1 charges for the iodates and 5 uncharged sulfur dioxides. So total charge of -2 on the reactant side. On the product side, I have uncharged iodine and 5 -2 charged sulfate ions. So a -10 total charge. And now comes the part where we have to actually to change course. For acid, we add H+. For base, we add hydroxide. So for our acid reaction, we are going to add H+. So we need to add 8 H+ ions to turn that -10 into a -2 and get it to match up with this -2. Adding 8 H+ means we're going to have to add 4 waters to balance out the hydrogen. And so our reaction in acid is going to look as follows. Two iodate plus 5 sulfur dioxide plus 4 water makes iodine and 5 sulfate and 8 hydrogen ions. If this was in base instead, all that really changes is this last step. Where we would be adding hydroxides instead of hydrogen ions. So we would add the hydroxides to the less negative side. So 8 hydroxide ions, which would give a total of -10 to the reactant side to match up the -10 on the product side. And then to counterbalance those hydrogens, I would have to add 4 waters. And so the reaction in base would be, again, practically identical, just one different component. 2 iodates and the 5 sulfur dioxides and the 8 hydroxides making iodine, 5 sulfate ions, and 4 waters. So like I said, the real trick, the hard part here is in those first couple of steps. Once you get to that part and you get through here, the last part's relatively simple, and it really doesn't matter which direction you go. It falls into a relatively predictable kind of pattern. Any questions about example 8 here?
No.
No.
All right. Let's take a break then. It's 10:03 according to my watch. Let's come back at 10:15, and I'll do a couple more examples. I'll also show you the half reaction method, which is an important method to know, and it's an alternative in case this has been a little bit confusing for you. So let's take 10 minutes, just stretch out and rest our brains for a minute, and we'll come back at 10:15. Spend at least some of this time talking about the half reaction method. So this is the alternative method that can be used for balancing oxidation reactions. Now, like I said, this does have some utility in terms of electrochemistry. If you have to take Chem 2, you will see electrochem in that course. Redox reactions will be part of that because redox reactions run electrochemical reactions. And this is the way that they are presented in terms of these half reactions. But in terms of the balancing of equations using this method, what you'll find is that it is considerably a longer process. And so if you look at the process itself, there are 5 primary steps. Now, I say that a little bit tongue-in-cheek because step 3 here has many sub-steps within it to balance each half reaction in total and in turn. But it can be done. And so the process starts the same way. We start with oxidation numbers. We then use those oxidation number changes to split the reaction into half reactions, an oxidation half reaction and a reduction half reaction. And then our next step is to balance those half reactions, multiply the half reactions to make sure that the number of electrons coming in and the number of electrons going out are the same, and then do any kind of cancellation that is necessary. And so let's kind of get into the process a little bit here, and I'll kind of show it off. So for balancing, there are actually different procedures for balancing in acid versus balancing in base. So what I'll do is I'll show you the directions for how to balance it in acid, and then I'll show you how we tweak those directions just slightly to balance it in base. And so for balancing in acid, what we do is we first start by balancing everything that's not hydrogen or oxygen. Then we balance the oxygens using water. We balance the hydrogens using hydrogen ions, H+, and we balance the charge using electrons. And so we would do this for each of the half reactions. And then we'd go back here, and once we had our half reactions, we would multiply them to make sure that the electrons that are being left out by the oxidation are being taken in by the reduction. And then we add them together and cancel anything that's common on both sides. Now, if we are in base, it's very, very similar. The only difference is that at the very end, and I'm talking the very end, this step 5 end, at the very end, we simply convert the hydrogen ions and hydroxide ions and interchange them with each other. And how we do that is we add equivalent amounts of hydroxide to each side. And so that's how we get it to remain balanced. The hydrogen ion combines with the hydroxide ion to make water. The hydroxide ion on the opposite side stays hydroxide ion, and we'll have extra water molecules left over, and we'll just end up canceling them out. So with that in mind, let's go back to the example set that we were working on. And do a couple of examples using this particular methodology. So this says that we're going to balance it in acid only. We're going to balance it in both using the half reaction method just to show it off. So our first step in this method is the same as the first step it was in the previous method as well, assigning oxidation numbers. So oxidation number for manganese here is +2. The oxidation number for the bismuth here is +5. And for the oxygen, it's -2. For the permanganate, manganese is 7. And oxygen is -2. And in the bismuth, it's a +3. So this is our process. We've got everything set up. Now we just need to break it up into half reactions. So for our oxidation half reaction, we can see that the manganese is going from +2 to +7. So that's going to be the reaction that we are starting with. Manganese +2 turns into permanganate MnO4 -1. And our reduction half reaction, leave a little space. Our reduction half reaction is going to involve the bismuthate ion, BiO3 minus, turning into bismuth 3+. So this is the reaction that's going on in both circumstances. Now our first step would be to balance everything that is not hydrogen or oxygen. And in this case, it's pretty easy. I have one manganese on this side, I have one manganese on that side, so that one's balanced. I've got one bismuth on this side, I've got one bismuth on that side, it's balanced as well. So that part's taken care of. Second step, I need to balance oxygen by adding water to the opposite sides. So I have 4 oxygens here. That would require 4 water molecules on this side. I have 3 oxygens here. That would require 3 water molecules on this side. The next step would be to balance hydrogens using hydrogen ion, H+. So I have added 8 hydrogens in total to the reactant side in the oxidation reaction. I'm going to need to add 8 hydrogen ions on the product side to counterbalance it. I've added 6 hydrogens in the form of water here. I'm going to need to add 6 hydrogen ions to the reactant side to balance it out. And then my last step is to balance electrons, to balance charge using electrons. So very similar to the process that we did before. I need to draw a line down the middle.
Mr. Brown.
Yes, Chastity.
Okay, it's a quick question. If it was hydrogen, if it was an equation with hydrogen, you would just need to add the oxygens? If it wanted it acid only?
So if it wants it in acid only, your first step is still to balance the oxygens. And if there were hydrogens on this side already, I would just take that off. So let's say that there was already, there's already 2 hydrogens over here on the reactant, right, or on the product side. I would only add 6 hydrogens instead of 8.
Okay. Go ahead. Okay, I'll process it.
Okay, so we're to the part where we're evaluating charge. Excuse me. On the reactant side, I've got a +2 charge from the manganese, and I've got 0 charge from the waters. So total charge on the reactant side is +2. On the product side, I've got a -1 from the permanganate and 8 positive ones from the hydrogen ions. Total charge over here is +7. And so I would need to add 5 electrons to this side to get rid of that extra positive charge. And so the electrons always go on the side that is too positive, that has extra positive charge. And so now I've got those charges to even out. I can rewrite my half reaction. My half reaction is going to be manganese 2 positive plus 4 waters makes permanganate ion plus 8 hydrogen ions plus 5 electrons. And so this is my oxidation half reaction. For the reduction half reaction, we've handled everything so far other than the charge. Total charge, I have a -1 from the bismuthate ion and 6 positive ones from the hydrogen ions. Total charge over here is +5. And on the other side here, I have a +3 for the bismuth and 3 uncharged water molecules for a +3 over here. To balance the charge, I need electrons. So I'm going to have to add 2 electrons to this side. And the 2 electrons are going to take that +5 to a +3 so that the +3s now match up. In a similar fashion, I've got everything balanced up. Let's go ahead and write the half reaction. It's BiO3 -1 plus 6 hydrogen positive ions and 2 electrons, making Bi +3, bismuth 3 ion, and 3 waters. Okay, and so with these 2 half reactions, this is, we've only gone part of the way. We are now through step 3 of our 5-point procedure that we talked about. The next step is we have to evaluate the number of electrons that are leaving the manganese versus the number of electrons that are coming into the bismuth. And we can see that the 2 are not equal. 5 are being deposited by the manganese, 2 are being turned into the bismuth, and so we need to equal it out so that just as many are leaving as are coming in. And just like we did in the previous method, the way to do that is through a lowest common multiple. The lowest common multiple between 5 and 2 is 10. So I'm going to multiply both equations by a number to get them to 10 electrons either gained or lost. And that means that I'm going to have to take the manganese half reaction, multiply it by 2, and the bismuth half reaction and multiply it by 5. And so what this will look like afterward, 2 manganese +2 plus 8 water makes 2 permanganate ions, 16 hydrogen ions, and 10 electrons. And if we add that to our other half reaction, 5 bismuthate ions and 30 hydrogen ions and 10 electrons make 5 bismuth 3 plus ions and 15 waters. Those are our two half reactions. Now we can see that I have equal amounts of electrons on each side. Since I have that, I can now combine them together, and I'm actually going to have to put the result down a little bit lower here because it's going to take up a lot of space. So the net result, which we'll put here in black, is 2 manganese positive 2s, 8 waters, 5 bismuth 8 ions, 30 hydrogen ions, 10 electrons, 2 permanganate ions, 16 hydrogen ions, 10 electrons, 5 bismuth 3 plus ions, and 15 waters. This is the balanced equation that we would run into. Now, there is some extraneous, there's some fluff here. There are things that are common on both sides that would be in our best interest to get rid of. In particular, we can look and see that I have water common on both sides, I have hydrogen ion common on both sides, and I have electrons common on both sides. So similar to what we saw in net ionic equations yesterday, we are going to want to cut some of the things that are common because they cancel out. So the 10 electrons can cancel out. Let's see, I have 8 waters on the reactant side that can negate 8 of those 15 waters on the product side. So that 8 becomes a 7. And I've got 16 hydrogen ions on the product side that can negate 16 of those hydrogen ions on the reactant side. And so if I do one more rewrite here, the final equation in acid is 2 manganese ions, 2 manganese 2 plus 5 bismuthate ions, plus 14 hydrogen ions make 2 permanganate ions, 5 bismuth 3 plus ions, and 7 waters. That is the final, at last, equation for this reaction in acid. So, like I said, individually, oxidation half reactions, reduction half reactions aren't too terribly difficult to do. And even in the combining out process, this isn't terribly difficult. There is a reason why this method is preferred by some students and by some faculty members for that matter. The bottom line is the hard part is really there's a lot of process. There's a lot of steps in here. It took us 20 minutes to do this problem. Whereas in the same light, we did in 20 minutes acid, base, and part of a third reaction using the other method. So there is some utility to this. Don't get me wrong. I'm not going to completely bash this technique, but it is a good bit deal longer. And there are lots more steps to do, lots more mistakes that can be made along the way. And we haven't even done the base part. For the base part, if we take this equation up here, to convert it into base, what I need to do is there is no H plus, or at least very little H plus, available in base. So what we do to more or less combat that is we're going to add equal amounts of hydroxide to each side of the equation. When we do that, it's going to turn the hydrogen ions into waters. And the second thing it's going to do is it's going to create another situation where we have to cancel because I'm going to have waters on each side. So these 7 waters negate 7 of those waters. And so the net result for base would be 2 manganese, 2 pluses, 5 BiO3 minus bismuthate ions, 7 waters, making 2 permanganate ions, 5 bismuth, 3 ions, and 14 hydroxide ions. And so once you get it in acid, turning it into base isn't usually that difficult. Sometimes, if we find that our hydrogen and our water are on opposite ends, literally all that happens is that it flips around. The waters move over to the reactant side, the hydroxides move in equal and opposite number to the product side, or vice versa. Where it gets a little bit complicated and tricky, there are some occasions because of hydrogen content in some of the reacting species where water and acid end up on the same side of the equation, and then that's the case where you can't do that. And you have to actually go through and do the math. But if hydrogen and water are on opposite sides of the reaction, then literally all they do is switch places, and the H plus becomes OH minus. And that's how you fix it for a base as opposed to an acid. All right, any questions about this problem?